Hi folks, thanks to be here for this talk about an introduction to stream processing. I'm Nicolas Frankel, I've been a developer for 2 decades and I'm a recent developer advocate. Our schedule for today is mainly structured around the following points. The first one, why streaming? And in order to understand why streaming, we will go back in history for quite a long time. And then how, once we've got streaming, we can leverage data, and especially open data. Finally, I will try to impress you with a demo. So when I started my career a long time ago, all data was stored in SQL databases. And it has some implications. The first one is, first, we don't want duplication. You've learned when you were taught SQL that we don't learn duplication, because when an entity has a relationship with another entity, then if multiple entities have relationship with the same entity, we can just change the data with the related entity and all will magically appear to have been updated. If you duplicate the data, and for example, you have, I don't know, the address of a company that is referenced like in some other entities, and you need to change the records of the address of the company, you will need to change it in every record. That we don't want to do that. There is also another reason that is less talked about, is at the time when SQL systems were designed, storage was quite expensive, and so duplication of data was just taking space for nothing. Another implication of SQL is we actually want data quality. So we put constraint to say, hey, this is a date, this is a timestamp, this is a voucher of 20 or whatever. So you put as much constraints as possible on your model so that you are sure that it conforms to your design. But actually, when we think about it, this is all designed for writing. We think about writing. And in some cases, that's not really what interests us. Is when you're reading stuff, that's not interesting. When you read stuff, you probably want to be fast. And if you have SQL with joins, especially when you've got many joins over several tables, that slows you down. And so it boils down to, I want data to be correct versus I want data to be quickly available. And let me tell you about 2 use cases that I believe are quite interesting. The first one is analytics. I worked at some point in retail, and one of the common requirements in retail is to have some analytics over the previous hour in general. So imagine you are a supermarket director and you've got a big stock of bananas, and it's Saturday, and on Sunday you won't be open, and you know that if you don't sell your bananas on Saturday, on Monday you will need to throw them out because they will be too black for selling. What you want probably to do is to have the analytics of your sales of banana, so that if you don't sell enough, you can provide some discounts. So hourly, you will need to ask your IT department for the statistics and then check hour by hour. And you want that data as fast as possible, of course. And then there is reporting. In general, you have a bank, and I don't know about your country, but in France, you receive every month, you receive your bank account with your the operations, the credits, the debits, and the balance. And for that, again, it will be done at the end of the month. It needs to be as fast as possible because you have a lot of customers, and you don't want your accounts to take too long to compute and then to print. And so for that reason, we invented the concept of ETL, of extract transform load, because you have different actors and different needs. And in that case, it doesn't stand to reason to use the same database. So you've got your transactional database. You will extract the data, you will transform it so that there is no more join, you don't care about duplication anymore. The idea is when you load it into this new database, then here you can execute queries that are meant to be very, very fast. And the thing is, there is also another reason, is if you have the same database for transactions and analytics, then you will put additional load on the database. And in general, databases, they scale up to a point, especially SQL databases. We will see later, they were not designed to scale horizontally, they scale vertically, and then you are limited by hardware or software. So the idea is, what does this extract transform load? How is it implemented? Well, batches. Batches are everywhere. I believe even if you are a junior in the industry, you've probably even now have been confronted by batches. And so they have interesting characteristics. The first thing is they are scheduled at regular intervals. Like I mentioned, the supermarket analytics every hour, or the monthly statement by the bank monthly. And they run in a specific amount of time. And you see probably where I'm heading at. You've got some issues sometimes. The first issue is that when you design your batch, you have this schedule in mind, and so you take great care that you don't overlap. So if you need to run every hour, you take care that it runs let's say 30-40 minutes top most, and gives you a buffer. But in general, data increases over time, and the ops people, they are checking carefully that the time it takes to execute the job actually increases over months, years, or whatever. And at some point, there is a chance that the time it takes to run your job is actually longer than the scheduled period. And even if it's not the case, if your batch takes, let's say, 40 minutes for a batch that is scheduled hourly, what if it stops for whatever reason, if it fails at 35 minutes? 35 plus 40 means you will again go over the period. And sometimes also what happens, again, with the increase of data, is that the space it takes in memory exceeds the capacity. For the later points, that's quite easy. We keep a cursor, so we don't handle everything. We just handle a slice of the data, and we manage chunks of data. And of course, it's only possible when data is, we don't need to do validation of data of different chunks. Then there is a new problem, is what about new data? For all those reasons, we wanted something to scale horizontally. And again, the SQL systems, they were not designed to scale horizontally. The idea was, hey, we don't have much data. Well, we didn't at the time, but we want data to be correct, to be true. And so the whole idea behind SQL databases is this. We want data to be correct. And you can scale up to a point. Big data said, okay, we mostly want data to be correct, but the most wanted characteristic we want is we want to scale. And we want to scale, again, because of software and hardware limitation, we are limited with vertical scaling. We want to scale horizontally as much as possible. So the idea behind big data and NoSQL databases was we scale, like web scale. But of course, there is nothing like free. And the idea was we can scale as much as possible to have like write speed, but at some point you will need to read the data. So if you dump everything into your database and you don't do any checks, because of course you have constraints and constraints take time to check, then that means that the job of like managing, checking that the data is in the correct format is when you do the query. And so there is this tension between, hey, is it better to do schema on read or schema on write? If you want to be very, very fast when you write, then you probably do schema on read, but then you like move the problem and the time it takes to validate the data when you read the data. So you have very fast writes, but then you have slower reads. On the opposite side, if you design, and depending on your NoSQL database, it can be possible or not, if you implement constraints when you actually write, you slow down your writes, but you make reading so much fast. So be careful about that. Yes, you can be very, very fast in writes, but that means that your queries will be slower. But recently we saw another thing coming. And the idea is, okay, databases are meant to store stuff, but how do we handle data out of it? And the idea comes from an old paradigm in programming, which is event-driven programming. If you interact with a user interface, you probably have been confronted with events like, hey, instead of doing something at the time or whatever, the idea is you do something when something happens. Like when the user clicks a button, you do something. And so we can leverage that and say, hey, let's make everything event-based. And of course, there are a couple of benefits with that. The first, I told you about the storage space that might be too small to take all the data in memory. Well, if you've got one small event, then it becomes a no-brainer because the event is, of course, very small. Because of that, it's easily processed. And another side effect, which is actually very beneficial, it is instead of like every time like pooling data and pooling data, you actually are reacting to data. Data is pushed toward you. And data is pushed as soon as something happens. And so this is as closer as you get to real time. There is no such thing as real time because even light takes time to move from one point to another. And of course, we are talking about IT systems, so there will be like eventual consistency of data coming in, but this is still very close to even time. And it keeps like the derived data. So you have got the source of truth and you've got derived data. And if you have even streaming, it will be like as close to the source of truth as possible. So you will have like very much in sync, instantly, or again, near instant in sync properties. Of course, there are like not so good side effects. And one of the worst is how you think about it. Before you were thinking in batches, you were thinking in chunks. And now you think about streaming and it's never ending. So you know when you start your stream, you never know when it ends. Actually, it ends when you stop it explicitly. Otherwise, it's just an infinite stream of events. You've got also new characteristics. Before you were able to do aggregation on your batch. Now you can still do aggregation, of course, but since it's a flow of events, you need to explicitly design your stream so that if you want some aggregation, you need to define over which window of time you want it. And there are different kinds of windows. You can have like tumbling windows every 5 minutes, or you can have like sliding windows. Again, it depends on your needs, but you need to think about it. The idea behind streaming is quite easy to understand. The first is you've got sources, and the second is you've got sinks. And in the meanwhile, you will do some transforms, some enrichment, some ML inference. Now it's pretty hype to do some machine learning inference. And when you do enrichment, you probably want to have data available around. So not only in databases, because if you have data in databases, it will take time to fetch it, but it should be as close to possible to the stream processing engine if you want speed. And it opens a lot of new doors. Real time, I was talking about real time. Let's get back to my example of the supermarket director. Supermarket director wants the data as soon as possible. He actually don't want the data hour by hour. But this is how we design the system, because when you only have batches, you need to say, hey, I want the batch to run every hour. If you want to think about correctness, there is a first issue. The first thing is, if we run the batch every hour, the batch is not instant. It will take some time to get the results. So let's say you will need to run it every hour, and then you will get the result at h plus 1-2 minutes, whatever. I don't care. So regarding correctness, this is not correct, because we want to have the data as fast as possible. But it's even not that is the biggest issue. We need to wait the full hour to get the results. Now imagine if we could get the result like 5 minutes before the hour. Not much can happen in those 5 minutes unless you've got, I don't know, like somebody who like is crazy about bananas and buy 10 kilos of bananas, but probably that won't happen. Let's say the probability is very small. So most of the time you want data as fast as possible, and you don't need to complete the full cycle to act upon it. Now, if you've got a stream of events, you will get data as soon as it comes, and you can already have some interesting insight about your data. You can see the trend of selling your bananas as it progresses, and you can make decisions as soon as you want. And, well, again, as I mentioned, imagine you have some learning model, some machine learning model. If you push this data to your machine learning stuff, then you can make some predictions again in close to real time. So I believe those are huge benefits. Now, where do we store our events? In general, right now, it's pretty popular to have dedicated places. Of course, you can store your events in memory, you can store your events in traditional databases, but it's better to have a dedicated system. Right now, Apache Kafka is pretty popular. You can also use Apache Pulsar, which is quite similar with some additional properties. And the idea behind Kafka, again, is distributed. It stores the data on the disk, and you can replay the events. So if you can have different consumers, and some of them might be slow consumers, some of them can be a fast consumer. Every consumer keeps track of their own offset, and so you don't need to send data at a dedicated pace. Every consumer has its own pace and can read data at its own pace. There are a couple of in-memory stream processing engines on the market. There are like on-premises ones, like Flink or Hazelcast. There are cloud-based ones, such as Kinesis or Dataflow. There is also an interesting project called Apache Beam, which is meant as an abstraction layer over like some of the previously named stream processing engine. Of course, it's not perfect because it's an abstraction, so it's leaky, and there is no standard regarding stream processing engine, but I think it's an interesting initiative to mention. Couple of words about Hazelcast, since I will be using it in the demo, but most of what I will tell later can be applied to any stream processing engine. The first is it's open source. We have a unified batch and streaming API, and of course we have also an enterprise offering, but what I will show you afterwards is entirely open source and free. There are two concepts, and I will use the semantics of Hazelcast, but actually the concepts are like very widespread. There is a concept of the pipeline. The pipeline is code or configuration that tells where you will read from, what steps of transformation you will like execute the data on, and where you will write to. And once you've defined that, you probably have a client that will take this code and send it to the stream processing engine. The stream processing engine receives it. It knows about the topology, it knows about the code, and it can distribute the loads over the nodes depending on the topology. And then when that happens, that becomes a job. Hazelcast has two deployment options. The first one is embedded mode. If you are a Java developer, that's pretty good, because that means that you can use Hazelcast just as a library. You just use it as a dependency, Maven or Gradle or whatever. So you put it on your class bus, you start a node, and then there is an auto-discovery mechanism that the nodes will check there are other nodes on the same network, and they will form a cluster. This is good to start with. However, of course, then the loads of the application plus the loads of Hazelcasts might not be compatible in a single JVM. So in general, when you start relying on Hazelcast as an infrastructure component, you probably want to go to the client-server mode. Client-server mode, you have dedicated nodes, and you can, of course, run a shell script, but probably you will want to use our containers or even run it on Kubernetes. We have Helm charts or operator. And then your application acts as a client of the cluster. And the good thing with that is that then you are not bound by Java anymore. We have several client APIs such as Node.js, C#, .NET, C++, Python, and Go. And the platform itself is pretty similar to what I've shown you before. You've got readily available sources, readily available targets. Because Hazelcast also is an in-memory data grid, you can load data beforehand so that the enrichment process is much faster. And something that I forgot to mention is we've got an API, so if there is no connector, and in the demo I will show you how to read data from a web service, for example, you can actually create your own connector. So now that we have stream processing in place, we want to use data. And of course, you will probably use data from your company, but if you don't have data, there is something very interesting, an initiative called Open Data. And Open Data is to data what open source is to software. So it's data that is freely available and that you can leverage. Depending on the part of the world you live in, there might be some initiatives managed by the government or the state or whatever. So here are a couple of initiatives in Europe, since I live in France. But actually, I will be leveraging an open data endpoint in California. There are some challenges to open data, and actually this is not related to open data, but to data. It's just that open data increase these challenges. The first is when I tell you about data. If you are a developer, you probably are thinking about web service, which is a good thing. If it's public data, if it's open data, in general, administrations, they don't have web services because they would need maintenance and whatever, so you will need to download the file, which is not great if you want to do data streaming, because again, you need to download it at regular interval and blah, blah, blah. If you think open data, you probably mean open formats. Well, that can be far from the truth. Lots of data that you find provided by public administrations is in Excel format, and not the new open Excel format, but sometimes it might even be the old proprietary binary Microsoft format. Then what standards is the data provided in? I would assume XML, but then even if you provide XML, what's the grammar? We probably need some grammar. Most of the time you don't get that format, so you need to read either the documentation when it exists, or just infer the documentation if it doesn't exist. Data correctness. You probably have heard a lot of data scientists that tell that most of their work is actually not doing data science, but doing curating of the data. And that's, for example, in one of the data files I will have in my demo, you've got a line with, here is probably a time, here is a time also, and I know what this time means. This one is probably, what should I do with it? So, of course, there are a couple of solutions. First is discard the data if you don't need it. If it's a schedule, it will be harder to do. Or say, okay, it will be like after the day. So here it's not 24 hours 53 on day X, but 53 in the morning on day X plus 1. That's what I infer, but I'm not sure. I will be using for the demo something called the GTFS, because I want to have a demo from public transportation. And this is interesting because this is not a public specification, or let's say it's not provided by a public organization, it's provided by Google. But it's still interesting because it seems some of the organizations are using it nonetheless. It's based on two kinds of data. The first one is static data, and static data is data that doesn't change often. Here, a bus station, for example, bus station might change sometimes, but not regularly. So for static data, you will download files regularly. And you have dynamic data, and of course, dynamic data is the position of the public transport, and this changes regularly. So here is a very, very high overview of the dynamic model. This is the route message, this is what you get, and this has multiple feed entities, and each feed entity can have a vehicle position. This is what is interesting to us, because this is what I want to show on the map. The data provider, as I mentioned, is from California. Before I used the Swiss one, they changed their format, so I cannot use it anymore. That's why the GitHub repo is called Jet Train, and now it will be about buses. The pipeline is the following. First, I will read from a web service. Now, afterwards, I need to split, as I mentioned, I've got a huge envelope. I need to split it into updates. Then I transform it into JSON format. I need to filter out malform data. That's very, very important because every time my application fails, it will stop the stream. So I don't want to do that. Then I will do some enrichment. And as I mentioned, I have static files for that because the event is normally self-contained, and it references with ID or whatever other stuff. So here it references the top time, the trip, the routes, and whatever. Then because of front-end requirements, I will transform the hours into timestamp. Then I will need to flatten the JSON. Again, this is for front-end requirements. I don't want to have like nested JSON. I want to have as much as possible everything flat. I want to peek because I want to make sure that everything works as expected. And if it doesn't, I want to have some logging. If I log everything, there will be a lot of logs. So I will do some sampling on the logs. And then I put everything into in a map, in an in-memory map. So I need first to transform it into a map entry to say, hey, this is the key and this is the value. The key is the ID of the event. The value is, of course, the JSON payload. The architecture overview is the following. So I will have like a stream processing engine. Here I'm using Jet, of course, ready. And then at some point, I will have a loader pipeline that will run, and it will read the data files that I've previously downloaded. It will transform them, put them in JSON format, and put them, each of them, in a dedicated map. Then, when I'm ready, when this is finished, I will have another loader that will actually launch a new job. The new job will read the open data endpoint and will go through the pipeline that I've shown you before with all the steps, and then store the data in JSON format. Then a third component will actually register to changes, and every time there is a change, I have some front-end magic, and I'm not a front-end developer, so I relied on a colleague to actually display that on a map. So I've talked a lot. Now might be time to do some coding, or at least to show you how it works. So here I'm using IntelliJ, but actually you could do the same with jars and containers and whatever it is. Here it's easier for me to show you the code. I'm starting a Hazelcast instance, and now I can load the static data. So I have a module for that, load static. Here I will run it. This is by far the most complex part, because every file is pretty similar. So I've tried to factor a lot of code together. So I don't want to show the code. Well, I will give you the link to the GitHub repo at the end, but the code is the most complex. So we will just check that everything has been loaded. Yes, it seems everything has been loaded. So now the idea is we can launch the dynamic data. So stream data. This is much more interesting and easier to read as well. So here I have, oh, not this one. I have the main method. So here we don't have no framework, nothing, is just a library. And here I will do the pipeline as I mentioned. So let me show you. Here I create a client with the Jet instance running, and I will launch a new job with the pipeline. The pipeline actually will read from a remote service. We will add the timestamps, and here you can see all the steps that I've told you before. So we will extract the entities, map to JSON. We will do some data curation. We will map, so that means enrich with stuff that is already stored in memory, and this stuff is data from the static files. Then an enrichment that's a bit more involved, so we need to use another primitive, and again we change the time, we transform the time to timestamps, we map it to a flat data structure, we peek, so that's something that you might see here. I will do some picking, so something is happening, not every time, I don't work every time, but as much as possible, without overflooding my console. And finally so now I have this running, I will start the web application, and let's see how it works, how it displays. So now the web app is reading from the in-memory data grid, and if we go closer to the map, you can see that it reads from the memory data grid. So there will be on the front end a schedule, because if I do it as fast as possible, I will overflow my front end browser. And so what happens is that it gets the value at time X, it knows the value at time y, and meanwhile, when it doesn't receive data, it will like compute the place the bus or whatever should be. And then when it receives the new data point, it sets it at the correct place. So here you can see that the schedule is perhaps a bit fast, but here seems to be much better. I know. There is also an issue with this demo so far is I'm not leveraging one of the file I'm receiving, and the file is the route. So actually, is the path. So when I've got two stops, the stops might not be in a straight line, and probably they are not. So in general, you would have a path that tells you where the bus goes through, and here I'm just interpolating that is just like a bird in a straight line coming from one stop to the other. I need to do that since a couple of times, but my front-end skills are pretty low, so far I didn't manage to use it. It still gives you a nice approximation of what is happening. Okay, so this is the end of the demo. Recap. So, compared to batch, streaming has a lot of benefits, as I've tried to show you. And if you've got data to leverage, so much the better. If you don't have data, just go and check. There is open data, endpoints everywhere, and you can leverage it to do pretty cool stuff. So thanks a lot for your attention. You can read my blog, you can follow me on Twitter. We've got documentation on what I've shown you. You can check it here. We've got a GitHub repository. So if you are interested in the code, because I didn't explain everything, you can check the code by yourself. And if by some chance I've got you interested in Hazelcast, we've got a Slack, please join us. Or if you are shy and don't want to interact, get some free training first. Again, thanks a lot for your attention and have a good day.